Welcome to Study Loop.
This is a question about angular momentum in the solar system. In this question, we should assume that all planets orbit the Sun in perfectly circular orbits. Then, because of that, the angular momentum of each of those planets in orbit is given by this expression. So the angular momentum is equals to the mass of the planet times the velocity of that planet times the radius of the orbit. In the first item of this question, we have to derive an expression for the orbital angular momentum as a function of the mass, the radius of the orbit, and the period of that orbit. We begin by rewriting the original expression. So the angular momentum is given by the mass times the velocity times the radius. We want to eliminate the velocity. For that, we can use this expression, which tells us that the velocity is equal to the angular frequency times the radius of that circular movement. Therefore, we can say the following. The angular momentum is equal to the mass times the angular frequency times the radius squared. Squared because we already have a factor of r here, and there is an extra factor of r when you substitute v by omega times r. Now remember about the relation in between the angular frequency and the actual frequency in units of 1 over time. That relation is the following. The angular frequency is equal to 2 pi times the actual frequency in units of 1 over time. Using that relation, we can say the following. The angular momentum is given by the mass times 2 times pi times the frequency times the radius of the orbit squared. Now, there is a relation in between the frequency and the period. That relation is the following. The frequency is the inverse of the period. Then, using this equation, we get that the angular momentum is equals to 2 times pi times the mass times the radius squared divided by the period. And this is the expression that the first item of this problem was asking us about. In the second item of this question, we have to apply this expression to all the 8 planets of the solar system using the data that is available in Appendix F. Making it easy for both of us, I had already separated all that data right here. So let me put it here so that we can see. Now all you have to do is fill this column using this data and the equation for L. As an example, let me show you how to perform the calculation for Mercury. So it goes as follows. The angular momentum L is equal to 2 times pi times the mass of Mercury, which is already in kilograms. So we have 3.30 times 10 to 23 times the radius of the orbit squared. The radius of the orbit is already in meters, so we just have to plug it in here. Then 2.44 times 10 to the 6th squared divided by the period of that orbit. The period is in days, it's not in seconds, so we have to convert when plugging in. The conversion is fairly easy to perform. So we have 88 days, but each day has 24 hours, but each hour has 60 minutes, and each minute has 60 seconds. Then it's already converted. By solving that calculation, we get a value for the angular momentum that is approximately 9.14 times 10 to 38 kilograms meters squared per second. Now all we have to do is repeat this process to fill this column. By doing that, we get the following. And this is the answer to the second item of this question. Just a small advice. Here we have several orbital periods which are in years and not in days, so the conversion process, although similar, is not exactly the same. Converting from years to seconds goes as follows. 1 year has 365 days, each day has 24 hours, each hour has 60 minutes, and each minute has 60 seconds. The only difference, as you can see, is an extra factor of 365. As long as you'll be careful with this conversion, you should have no problem in arriving at these results. In the third item of this question, we have to evaluate what angular momentum the Sun has due to the rotation about its axis, again, using data from Appendix F. In Appendix F, you can find the mass of the Sun and the radius of the Sun. On top of that, the problem gives us the rotational period of the Sun. To solve this item, you have to remember that The rotational angular momentum is given by the product in between the moment of inertia and the angular frequency, and this is our starting point. So the rotational angular momentum of the Sun about its own axis is given by the moment of inertia of the Sun times the angular frequency of rotation. Now, for the moment of inertia, we assume that the Sun is a uniform sphere. In that setting, the moment of inertia of the Sun will be given by this expression, which is just the moment of inertia of a uniform sphere. It is 2 times the mass times the radius squared divided by 5. Then, here we have 2 times the mass of the Sun, let me call this ms, times the radius of the Sun squared divided by 5. Now we multiply by the angular frequency of rotation. The angular frequency of rotation is nothing else than the interval delta theta that the Sun rotates and the time it takes for the Sun to rotate by delta theta. Now, we want a complete rotation. Then delta theta is equals to 2 pi radians. So here we have 2 pi. And how much time does the Sun takes to make a complete rotation? Well, we call that interval of time exactly the period. Then we reach the conclusion that the angular frequency of rotation is equals to 2 pi divided by the period. Now, all we have to do is plug in the values that we have and get our answer. So the orbital angular momentum is given by 2 times the mass of the Sun, 1.99 times 10 to the 30, times the radius of the Sun squared, 6.96 times 10 to the 8 squared, divided by 5, multiplied by 2 pi, and then divided by the period of rotation. That period is of 24.6 days, but we have to convert it into seconds in order to use in this equation. Then converting from days to seconds goes as follows. 1 day has 24 hours, 1 hour has 60 minutes, and each minute has 60 seconds. Then we multiply the number of days by this conversion factor to have it in seconds. By solving that calculation, we get approximately 1.14 times 10 to 42 kilograms meters squared per second. And this is the answer to the third item of this question. Before proceeding to the next item, I have to organize my board a little bit. In the third item of this question, we have to compare the total angular momentum of all planets together with the angular momentum of the Sun. We begin by calculating the total angular momentum of all planets together. For that, all we have to do is add all these values. By doing that, you get the following: 9.14 times 10 to 38 plus a lot of values plus 2.50 times 10 to 42. By solving that calculation, you get the following total angular momentum: 3.13 times 10 to 43 kilograms meters squared per second. Now we compare the angular momentums by taking the ratio in between the angular momentum of the Sun and the angular momentum of the planets. This results in 1.14 times 10 to 42 divided by 3.13 times 10 to 43, which is approximately 0.0363. Therefore, the angular momentum of the Sun is only 3.63% of the angular momentum of all the planets together. On the other hand, if we add all the masses of all the planets, we get the following. The total mass of all planets together is equals to 2.669 times 10 to 27 kilograms. But the mass of the Sun is actually 1.99 times 10 to the 30. Therefore, the ratio in between the mass of the Sun and the mass of the planets is given by 1.99 times 10 to the 30 divided by 2.669 times 10 to 27, which is approximately 746. That is, the Sun has 746 times more mass than all the planets together, but at the same time has only 3.63% of the angular momentum of all planets together. Finally, the answer to this item are the ratios in between the angular momentums and the masses. Before moving to the next item, I will have to organize my board again. Now we go to the final item of this question. In this item, we have to tell if our approximation for the angular momentum of the Sun is overestimated or underestimated, provided that the density of the Sun increases as we get closer to the center. This one is not difficult to answer. The idea is the following. Suppose that this is the Sun and there is nothing inside it. Now let me put a small point mass inside the Sun. Suppose that this point mass is right here, at a distance, say, small r to the center. Then, the moment of inertia of that small point particle will be given by the mass of that particle times the radius squared, and that's it. Now, suppose that we have another point particle that is closer to the center at a radius, say, r prime. The moment of inertia of that second point particle is m times r prime squared. Now compare them. As you can see, r is bigger than r prime, therefore m times r squared is bigger than m times r prime squared. What I'm trying to say is that a particle that is further away from the axis of rotation has a bigger moment of inertia and therefore a bigger angular momentum than a particle that is closer to the axis of rotation. The Sun actually has more particles that are closer to the axis of rotation than particles that are further away from the axis of rotation. It means that our approximation of the Sun as a uniform sphere is an overestimation because we consider that there were as many particles away from the center as there are particles close to the center, and this is not the case. There are more particles close to the center, and therefore there are more particles with less angular momentum. Then our approximation overestimates the angular momentum of the Sun. And this is the answer to the final item of this question.